All right, everybody, let's get started on 9.4. So this is on convergence tests. There she is. And we're gonna talk about the divergence test and interval tests. And I have different content than Ainsley might go over with you on Wednesday. So she'll have a different set of problems if she uses her lecture notes that she had. And you might like them better than mine, apparently. I already found out who it was. I asked who showed up to your SI. All right, so theorem. If the series, the sum of UK is convergent. You know what? I don't like using UK. Let's do AK. Is convergent. Then the limit as K goes to infinity of AK equals 0. Now, hopefully this makes logical sense to you. If we are adding stuff to something that converges, eventually what we're adding can't affect the total. And there's only one number you can add to another number that doesn't affect the total. The only number that does this is 0. Because remember, that's what a series is. This is a bunch of things added. And if it converges, it actually has a sum. But maybe you want a little bit more than that. Maybe a little logical argument is enough. Maybe we can do a proof here. What would S sub n equal? S sub n is A1 plus A2 plus A3 plus ... an minus 2 plus an minus 1 plus an. This part here, I can rewrite this as S sub n minus 1. It's the sum of the first n minus 1 terms. Does that make sense? So S sub n equals S sub n minus 1 plus A sub n. And that means S of n minus S of n minus one equals A sub n. Just keep picking a different spot in the room, don't you, Dalton? I know. That's what I said. You're in a different spot. So remember, S is like the limit as n goes to infinity of A sub n. If it converges. If it converges. And we're saying that the series converges.
Is that's fine. So
That should be the limit from the sum of 1 to n. There we go. My bad.
means that S of n equals S. What means S equals something? Yeah, S of n equals something, or is it?
S, no, it's the sum. Because n's going to infinity. If I didn't have the limit as n's going to infinity, it's just S of n.
Oh,
Like this is the sum of A sub n from 1 to n. We haven't done the limit part. I'm about to do that right now. So let's do the limit here. Limit as n goes to infinity of the left side, and the limit as n goes to infinity of the right side. But this is s minus s. The limit for as n goes to infinity is just the complete sum s. Both of those are going to go to infinity. So we have s sub minus s equals the limit as n goes to infinity of A sub n, and that must equal 0. S minus s is 0. And so we have shown that if it converges, the limit is 0.
What are you saying that the phone has convergence you would be considering?
If it converges, yes. If the series converges, then the limit is 0. This does not say the limit as k goes to infinity of k sub A sub k equaling 0 means or implies that it's convergent. We saw last week the harmonic series. The harmonic series 1 over n. Well, the limit as n goes to infinity on that does equal 0, but the harmonic series diverged. So the limit equaling 0 doesn't guarantee convergence, but convergence guarantees the limit is 0. So take away from this, not a two-way theorem. But that is not the divergence test. That's just something that's kind of like the opposite of the divergence test. Everyone ready for some more? Does anyone need it longer? I'm about to take it. All right. So the corollary to that theorem is the divergence test. If the limit doesn't equal 0, then the series k equals 1 to infinity of a sub k diverges. So adding in what we just said. So if limit is a sub k equals does not equal 0, it diverges. And putting in words what I just said as a note on the last one, if the limit is a sub k does equal 0, this doesn't show convergence or divergence. Examples are so much better than this shit though. Right? But we gotta kind of give you a what the hell are we talking about thing first before we can do that. So there's your what the hell are we talking about thing. Let's do some examples. Let's do the sum from n equals 1 to infinity. N minus 1 over n plus 1. And let's see what is revealed by doing the limit. The limit as n goes to infinity of n minus 1 over n plus 1. That is going to infinity over infinity. And what does that mean? What? Say it again. I can't hear you. You're talking quietly. It's indeterminate, yes. And what can we do about indeterminate? L'Hopital. So we'll take the derivative of top and bottom separately, and we get 1 on top and 1 on bottom. So the limit equals 1. And that falls under the first half. The limit as n goes to infinity of a sub n does not equal 0. Thus, n equals 1 to infinity of n minus 1 over n plus 1 diverges. What about? Limit as n goes, not limit, we're doing a series. N equals 1 to infinity, 1 plus 1 over n to the nth power. Let's take a look at the limit again. Limit as n goes to infinity, 1 plus 1 over n to the n. What does that equal? What? I think it does equal e. It doesn't equal 0, right? How can we check that it equals e? The calculator does this. All right, so let's say the limit is n goes to infinity of y. So y equals 1 plus 1 over n to the nth power. And the limit's still doing applying to both sides here. Limit's still on both sides. Because things inside a limit work just fine. We can take the natural log of both sides and it's still gonna hold true. And properties of log say we can pull that bastard down, right? That exponent can come down. They don't really want the derivative here. So used to doing derivatives with this. If we raise both sides back to the power of e, we get y equals e to the n times e to the ln of 1 plus 1 over n, which is just e to the n times 1 plus 1 over n. So now if you look at your limit as n goes to infinity, I'm not getting e, I'm getting infinity. Is that another, what did you put in your calculator exactly? Did you like do a limit thing? Does it do limits? Oh, yeah. Okay, so doing one of them generates an E, but we're adding E a bunch of times. So yeah, is it? If you look at one, like 1 + 1/x to the x power, that does equal E. But like doing a series, we're adding them all up, so it's a limit thing. But this is going to infinity, right? Because that goes to infinity, which means this goes to 0. And I've got 1 times e to the infinity. E to the infinity is infinity. So it diverges also. Summation of n equals 1 to infinity of 1 + 1/n to the n power diverges. Now, I think we could have argued that just as well up here. I only went off on the E thing because Dat threw me off by saying it was E, and I'm like, all right, let's show that it's E. This is 1 + 1/infinity to the infinity. That goes to 0. 1 to the infinity is 1, which does not equal 0. And we showed it diverge that way. So there was a shorter way to do that. But this is if you wanted to look at what 1 + 1/n to the n is without doing limits, you can kind of look at it that way. You do the natural log. You learned this in Calc 1. Whoever taught you had to have shown you 1 + 1/x. All right, you guys ready for more? Anybody? A couple people are still writing. Wait. All right, I don't see anybody right now. All right, properties of series. We'll have some more examples with divergence in a little bit. We'll look at some examples where we're like trying to find out what's going on. But we got some more tests we want to show. The summation of a sub k plus b sub k. Equals the summation of a sub k plus the summation of b sub k. And I'm going to show minus in there also. And I'm showing them separately. So if the summation of a sub k and the summation of b sub k both converge, then the sum of a sub k plus or minus b sub k also converges. If only one of them converges, then A sub k plus or minus B sub k diverges. Because we've got one divergent series there. If both diverge, the summation of A sub k plus B sub k definitely diverges. But if we look at the minus one, this is going to be like infinity minus infinity, or could be infinity minus infinity. This is indeterminate. So you gotta, don't just look at it in this form. You'll need to explore more. And I'll show you an example of that coming up. So if you add them together, but then add them separately, it should do the same thing. That seems like that should make sense. Only this last one is like, But then we get that whole infinity minus infinity, and you want to say that equals 0, but we saw that when you do the integral of x from negative infinity to infinity, we couldn't say that it equals 0. Which was kind of similar. Another property, so let's call that property A. Property B. The summation of C times A sub k equals C times the summation of A sub k. And if one converges, both converges. And the last one is kind of neat. If we have the summation of k equals 1 to infinity, or we could have like k equals 0 to infinity if this happens. No, let's stick with k equals 1 because I want to make sure that we hit cases that 0 doesn't fuck up. Of A sub k converges if and only if the limit or the sum of k equals n to infinity, A sub k converges. Remember, this is if and only if. And that's code for a theorem that works both ways. Works in both directions. And in other words, we can remove the first n terms. without affecting convergence. It does not mean that the sums are the same. If you've removed a couple of terms from the sum, you're going to have different values. But convergence goes together. And we'll go to do an example now. A fun example. Apparently you guys missed a really good SI session today since most of you didn't go. Ainsley's been working her ass off to prep for you guys. If you can make it, you'll gain something out of it. Especially on this. This chapter is the hardest chapter in all of Calc 1, 2, and 3. I think so. Chapter 15, the last chapter in Calc 3, is challenging. But these fucking tests, the tests we're doing today aren't too bad. You're going to get so many different fucking tests to decide divergence or convergence that you're going to be like, I don't know which one to use. And it gets fucking rough.
If we knew which one probably do better.
Sometimes that's not even helpful. Like you can eliminate which ones won't work, but then we'll get to like the comparison test is in 9.5. You got to find something that compares to that you can show converges or diverges depending on how you're doing it, and hope you ended up the right way. Like if it doesn't, you gotta. It's comparison test is probably the worst one of them all. You will not like this section. So if you've got time, I strongly recommend you go to her session. She's not going to lead you wrong. You know how I know? Anytime she's not sure of the answer, she's going over all this shit before she talks with you guys. She does way more prep work than I do. I read through my notes of another teacher that taught, these are the notes of the teacher that taught me. And I worked through a little bit of the ones that I'm like, I want to make sure I don't fuck that up. But like the next example, I didn't work through yet. I know it's going to work. I don't know what the answer is yet. She's going through and working through them all. And if she fucking finds something that's anomalous, she messages me and we work it out together. Just to make sure she's not leading you down the wrong street. You'll get some good prep out of it, or good workout, good gains out of attending your SI. She's gonna get a bonus later on. She works pretty fucking hard and it's fun. All right. You guys ready? I think that was long enough for you guys to finish writing that shit down. Let's take a look at find the sum of. Got to bring it down where I'm on the screen. Find the sum of k equals 2 to infinity. 2 over 3k minus 3 over 4 k minus 1. Now, if we try the divergence test here, try divergence test. You can always or see if it's not going to work. The limit as k goes to infinity of 2/3 to the k minus 3/4 to the k minus 1. Gonna be 0 minus 0, which is 0. So the divergence test doesn't tell us anything. Well, let's see if a little bit of manipulation here will help us figure some shit out. Well, first off, I'm gonna separate these into two sums. Oh, I said I was gonna separate them into two sums, and then I didn't. There we go, fix it. And let's look at them each separately. Let's call this one A minus B. So A, we're going to explore k equals 2 to infinity of 2/3 to the k. This is like k equals 2 to infinity of 2 times 1/3 to the k. What does that remind you of? Hopefully. The one person that went to the SI session answers it right away. Geometric series. But the geometric series starts at 0. And remember, it is A over 1 minus R. So how is this going to relate? This looks like A equals 2 and R equals 1/3. So the summation from k equals 0 to infinity of 2 of 1/3 to the k equals 2 over 1 minus 1/3. But I'm also going to write it as an expanded series for a second. If I do k equals 0, 1/3 to the 0 power is 1, times 2 is 2. And then if I do the k equals 1 term, what do I get? 2/3. And then rather than doing k equals 2, I'm going to go summation of k equals 2 of 2 to the 1/3 to the k. Because this is what we actually want. This is what we wanted for, that's our goal for A. So this clearly does converge, and we can get a value here. Let's see, this part right here is 2 over 2/3. If I multiply by 3/2 times 3/2, I get 3. And that has to equal 2 2/3 plus our summation. So doing a little subtraction, we will find that our summation has to equal 3 minus 2 2/3, which is 1/3. And that's part A. Why don't you guys take a few minutes and work on doing part B? Following a similar strategy of what I did here. Maybe we can together do the k-1 part first to make it look a little bit more like the other one. So, because that's going to throw some for a loop. If we're doing k equals 2 to infinity of 3/4 to the k-1, I don't like that k-1. It's fucking throwing off how I'm thinking. So I'm going to change it to n. I'm going to say n equals k-1. And that means if k equals 2, n equals 2, or n equals 1, 2 minus 1, which is 1. And I can rewrite this sum as n equals 1 to infinity of 3/4 to the n. And now that we're past that little hiccup of that first term, this might be a little bit easier. There's another way to do it where you start with the same k, but I think this is a little bit easier. And more useful in the big picture. As you take all the math classes here, like especially like differential equations and stuff like that, changing different series things is helpful. I have no idea. I told you I haven't worked this problem out. Michael thinks it's one.
I don't.
It might be. Did anyone else finish? Did you get one? All right, we got two people that think it's one. Dad's nodding his head. Let's give everyone else another minute and then we'll do it together and then we'll take a break. And hit the interval P series. So it should look like 3 times 1/4 to the m, which is also geometric. So let's look at what the geometric series would give us. N equals 0 to infinity of 3 over 1/4, or 3 times 1/4 the n, should be 3 over 1 minus 1/4. And that equals 3 over 3/4, which is 4, right? All right. But it also should equal the n equals 0 term would give me a 3 plus n equals 1 to infinity of 3 over 1 to the 4 n, 3 times 1 over 4 to the n power. So if we subtract, we'll get this. N equals 1 to infinity of 3 times 1/4 to the n is 4 minus 3, which equals 3. Now, another way you could have gone about doing this one, as a little sidebar, I could do k equals 2 to infinity, 3 over 4k minus 1, 4 to the k minus 1. If I multiply this by 4 over 4, I don't change the value, but it becomes 12 over the 4k. So you don't have to change the k away from k. And it should get the same thing. But we're doing k equals 2 to infinity here. Let's look at that way real quick. So that's 12 times 1. This ends up being, and I'll do the n equals 0 case, 12 times 1/4 to the k, which is 12 over 1 minus 1/4. Twelve times 4/3 is 16. But we need the k equals 0 term and the k equals 1 term. And then we'll have the k equals 2 to infinity, 12 over 4 to the k. K equals 0 is 12. And k equals 1 is 3. So 16 minus 15 still equals 1. So we would have gotten k, that value equals 1 either way. That was the value for B. We wanted A minus B though. Come back up here. A minus B was what we were looking at. So A minus B, 1/3 minus 1 is -2/3. So that's the end product of the entire series. And we found the sum. And it was negative. All right, let's take a 10-minute break and then we will do the integral test. Maybe I'll draw a red arrow going, pointing up here and point A equals 1/3 there and B equals 1 there. To show that. Let's say I was trying to conserve space or paper. Didn't want to do the next one line on the next page, it's just one. It also makes the next topic look prettier. We don't have shit cluttering up the top of the page. Right?
So maybe not.
Oh, you can, they call them wildfires now. They don't just say forest fire because it like will burn down planes and all sorts of shit. They don't want you to, they don't want you to just be careful with fire in the forest. They want you to be careful with fire. Don't fucking with me. You didn't want to interrupt lecture earlier, and that's why you sat in the back. I approve. Of course, I interrupted it by stopping and asking you why you're sitting in the back, but I appreciate the move. So Dad's got us going down a rabbit hole here because he's fucking apparently the Alice of the classroom. Like let's say we had k equals n to infinity of a to the rk. Rather than using n equals 2, I'm gonna just go k equals n. Or k equals 2, I'm gonna go k equals n. I could rescale this down to where k equals 0. If I wanted to restart with something, if I wanted to restart with like an m equals 0, I need k to be k minus n. Does that make sense? Because then if I plug in k equals n, I get 0, and that gets me to start there. Which means k equals m plus n. So I can rescale this or give it a new limit with m equals 0. Now starting at m equals 0 to infinity of a to the rm plus n, which is m equals 0 to infinity of a to the rm times rm, which equals r to the n, m equals 0 to infinity of a to the rm, which is going to equal r sub n times a over 1 minus r if absolute value of r is less than 1. So that's what he did here, but this would be a general form of what he's doing and why it works. Like, well, your intuition is right. I just showed like working another way how to do it. Get to the same thing. If you were doing n equals 2, so for what we had, 2k equals 2 to infinity, 2 over 3 to the k, or 2 times 1 over 3 to the k. I'm doing this where I should have, this was my n. I should have r squared times a over 1 minus r, but r was 1/3. 1/3 squared a over 1 minus r. 1/9 times, what do we have? Oh, 2 over 1 minus 1/3 equals 1/3. So that's a way of doing it without doing that, subtracting off. This is an alternate without having to subtract off. To not having to subtract A0 and A1 up to AN. This is probably easier for more than 2 terms, to be honest.
It started at like k equals 20, right?
Yeah, if we start like k equals 20, subtracting off 19 terms is gonna suck ass. But this is gonna work much faster. Now, I don't know if you would have intuited that with 19 different fucking terms missing, but you might have. Like, I'm impressed that you came up, you didn't come up with the general form, but you came up with the equivalent form of what was applicable here. You didn't know any of those, but now you have just been shown it. And maybe you'll remember. Maybe not. This is like, just like I did with the n minus or k minus 1, we can rescale where we start. I don't know if rescale is the right word. Change our starting limit. We can change our starting limit if we readjust our sequence, our series. So that's some good stuff. Good enough that I'm gonna scribble this shit down in my notes later on to make sure I add this in next semester. I was thinking this was the easiest way and subtracting off A0 and A1 was the easiest way. But I think doing the general form is much better. And it would have worked with the other one too, if we had gone all the way down to 0. So there is stuff to be gained from that. Maybe I should write a little flow arrow of what I'm doing here. Doesn't that look much better, arm rather than arc? M equals 0 to infinity gives A to the RM, AR to the M. So that reasoned this shit out all on its own. So stalk his ass and study with him. I was that desperate. And he spoke Hindi, and you don't speak Hindi? Do you have like a? Get captions or?
Didn't understand much, but I just thought that was so excited to have.
Also worth checking out if, like, I'm gonna flash over to it real quick. I don't have Discord on this, I don't think. If you go to our Discord, yes, I can access it through that. Let me, because I'm gonna show something you might find just as helpful. But it's gonna require ignoring that, go off that. Go to our Voldemortis Calc 2 Discord group. And if you click on resources, lol, I changed the recording. Let's try that again. I'm over here on ours. Click on Voldemortis Calc 2 Discord. You click on resources. Something she did today was from tutorial math.lamar. These are called Paul's notes. Paul's got great shit. Paul's got great notes for like the entire fucking sequence. If you visit the one she had, there's a whole bunch of weird fucking series and how to work with them and the solution on how to get them. And he's got like all sorts of fucking sequence. If we just look at series and sequences in general, we are doing the integral test in just a second. 9.5 is the comparison test and the limit comparison test. We will be doing alternating series tests. We will be doing root tests, ratio tests, absolute convergence. But if you go and look at him, he's got practice ones with worked out solutions. And you can find a link to it in Ainsley's resources. And just click on over to it and click on, like, it started at, go back. It started there, her link, but if you just click on series and sequences, you can get to more shit. And he's got like a whole bunch of different things worked out. We're gonna be doing Taylor series and shit like that after our next test, because I think it's better as its own topic. It's more of an applied subject than this convergence test stuff is. But you can, speaking of the special series, God damn it. Looking at some like weird ones right there. This, oh, he's got n equals starting at 2 here. Show all the steps. And he will walk through how to manipulate it around and do some shit like that. Okay. You may find it helpful as another resource that isn't a video, but you can read through it faster than watching a video. Let's go back to that. And I got to change the document camera over for the recording. All right, you guys ready for the integral test? The integral test, and this is gonna lead into the P series. P series. So the idea here is, and I'm going to shift over to Desmos in a second to show you it like clearer what's going on. The idea is if f of x is greater than 0, I did not write that. If f of x is greater than 0, there we go, now I wrote it. And f of x is decreasing. Then the sum of n equals 1 to infinity. f of n. And the integral from 1 to infinity of f of x dx should behave in a similar fashion. And let's look at two different series. We're going to look at n equals 1 to infinity of 1 over n. And we're going to look at, and give yourself some space on the page, n equals 1 to infinity of 1 over n squared. And we're going to explore on Desmos so you can see that what I'm saying is true. And then we'll sketch it over here where you can see it a little bit better, or have it in your notes a little bit easier. So this is doing n equals, like this is like 1 over n. I'm adding up the area underneath each line. So when n equals 1, the area under this box right under this orange line right here is 1. When n equals 2, this is 1/2 right here. You can see it's lining up with the 1/2. There we go. You can see a little better, lines up with 1/2. So this is like n equals 2. This is like n equals 3. How does that compare to 1 over x? So our sum is always greater than our integral value. Does that make sense? Like the first block is 1, but the sum from 1 to 2 of 1 over x is less than 1. N equals 2 to 3 is 1/2, but the sum of 1 over x from 2 to 3 is less than 1/2. Now, so 1 over n, I'm going to write, just sketch it down, you'll see it in a second. This is less than or equal to the integral from 1 to infinity of 1 over x dx. We'll see it in a second, but I want to do all the Desmos shit at once. If we look at, where is that? If I'm doing 1 over x squared. So that's the one I wanted right there, 1 over x squared. When I do 1, if I plug in n equals 1, I'm missing this first, like this isn't n equals 1. That looks like 1/4, right? That's 1/4. So this is like the n equals 2 box. So maybe I gotta throw that box in as well. So now this is like my n equals 1 box, or we'll take a look at it. We'll rewrite it as starting at n equals 2 in a second. But if we compare this to 1 over x squared, 1 over x squared is going to be greater than it for n greater than 2. Does that make sense? Because this is the n equals 2 line. That gives me a 1/4 height, or 1 over n squared. Let's see. I can't write on the screen with this because you guys can't see it. That's the 1 over n cubed for n equals 3. This is about 1/9. 1 over n to the 4th. and 16, 1/16. So back to the. Let me change the recording real quick. So I'm gonna write this one as like 1 and then do plus n equals 2 to infinity, because that's what the integral looked like of 1/n². And we saw that this. I already forgot how it looked. Who's the other sign? No, was it? The integral is greater. I have less than over here. Why? Why do I have less than? Let me look at that screen again. It does not. Yeah, this was less than the integral. This is less than 1 plus 1 to infinity 1/x² dx. And pictorially, we had n equals 1, 2, 3, 4. And we saw that this was it said 1/n was less than 1/x. It's not true. I think I wrote down the wrong damn thing. 1/n was great. This is 1/n is greater than. I showed it was greater than, and then I fucking wrote the wrong thing. So that's my 1/n in black, but my 1/x is doing this. That's starting at 1. It's going through those points right there. So that's 1/x. Well, going to infinity. But we're starting at n equals 1. And so we can see that the 1/x is less than the 1/n. And on this one, we had starting at n equals 2. We had our boxes. And this one was slightly above it. Over x². And so, like, if this diverges, if that diverges, then 1/n should also diverge because it's bigger, right? The integral from 1 to infinity of f of x dx diverges. This is in general. Then the sum of n equals 1 to infinity of f of n diverges. If f of x is less than, if this scenario holds true, if the sum is larger than the integral. i.e. n equals 1 to infinity of f of n is greater than 1 to infinity of f of x dx. And let's look at down here, n equals 1 to infinity of f of n is less than the integral of 1 to infinity of f of x dx. If the integral converges, then the summation converges. That's the idea of what's going on here. Putting in a nice little summary form. If f of x is greater than 0 and decreasing, on 1 to infinity, and f sub n equals a to the n, then n equals 1 to infinity, a to the n converges if and only if the integral from 1 to infinity of f of x converges. And we haven't looked at whether 1 over x or 1 over x squared converges or diverges yet. But we're going to do that in a second. We're going to do that with the p series. P series is magical. Does anyone need this up longer? Understood? Okay. So let's take a look at like the sum of n equals 1 to infinity of 1 over n to the p. And we are going to relate this to the sum of 1 to infinity of 1 over x to the p dx. And this might be a little bit easier to look at if I say x to the negative p dx. What type of integral is this? It's an improper integral. It's an improper integral because we have a limit of infinity. So I'll use a different letter here. Let's do m. Limit as m goes to infinity of 1 to m of x to the negative p dx. We can do that integral. If I go up a power, I've got negative p plus 1, and then divide by that power. That should say infinity. And this might look a little bit easier as x is 1 minus p over 1 minus p. That's another way of looking at it. I just rearranged them. So I've got the limit as m goes to infinity of m to the 1 minus p over 1 minus p minus 1, or minus x to the 0 over 1, which is minus 1. So this is going to converge. This will converge if the limit converges. One minus, I don't know. 1 to the 1 minus p. Thank you. Plugged in the wrong spot. But 1 to the anything is 1, right? Yeah. But yeah, I fucked that one up too. So when does this converge? So even if we have infinity to the 0.00001, that's still infinity, right? Like it's still going up and up and up and up. No matter what you plug in the calculator, you can plug in like a billion to that power and you'll have a number. But if you plugged in a trillion to that power, you'd have a larger sum. So like if 1 minus p is greater than 0, then the limit as m goes to infinity of m to the 1 minus p diverges. Does that make sense? If that exponent, if the exponent is positive, we're fucked. We're fucked. That's the official math terminology. You can look it up in any math textbook. It says you're fucked. What about p equals 0? Well, I'm sorry, what about 1 minus p equals 0? We're still kind of fucked, but because of the denominator, right? Well, the denominator fucks us on this one. So this boils down to if 1 minus p is greater than or equal to 0, it diverges. But that's not an easy way to remember it. We started with something to the p power. We want to end with something to the p power. So let's solve this for p. If I add p to both sides, I've got 1 is greater than or equal to p, or p is less than or equal to 1. P less than or equal to 1 diverges. What about p greater than 1? Well, now that makes my exponent negative. And one way of looking into that is that turns it into the limit as m goes to infinity of 1 over m to the absolute value of 1 minus p. We're making it negative, but I still want to show like a number there. And this is blowing up to infinity, which means this whole thing goes to 0 and it converges. Yeah, I keep writing 0. Apparently I don't like infinity today. This is called the P series. N equals 1 to infinity of 1 over n to the p is the P series. And this diverges if p is less than or equal to 1 and converges if p is greater than 1. Let's take a look at it. Some like that's the P series. That one's kind of easy. You just have to see it's in that form. A summation of, and this has got to match that. Our summation value has got to be the thing that's got the exponent on it. So let's take a look at some examples. Anyone need that longer? All right. Harmonic series. We already know the answer to the harmonic series. K equals 0 or k equals 1 to infinity of 1 over k. This is p equals 1, so this should diverge. Diverges by P series. But we can also show it doing the integral test. The integral test would be doing 1 over x dx. I want to leave it as 1 over x. This becomes the limit as n goes to infinity of the natural log of n from 1 to n. I'm getting ahead of myself. And this equals 0, and this is infinity, so this diverges. Next one we want to take a look at is the summation. Let's do 1 over or k equals 1 to infinity 1 over k, ln of k on bottom. I didn't show the divergence test up here, but the divergence test fails up here. Does it fail here? If I do the limit as k goes to infinity of 1 over k, or ln of k, the bottom goes to infinity, which means the sum is going to 0, and divergence test doesn't help. Fails to help us also. So we saw some examples earlier where the divergence test did help. But when it doesn't help, you can try the integral test until we have some more tests that we can do coming up. Let's compare this to the integral from 1 to infinity of 1 over x, ln of x dx. Now, both of these limits are going to cause problems. If I stick in 1, I've got ln of 1. This is, we got a 0 on the bottom. And if we stick in infinity, we've got infinity. So like, this is going to split 2 ways, but I think this problem might be a little bit easier if we do like a u sub first. So let's do u equals ln of x. So du equals 1 over x dx. And when x equaled 1, u equals 0. And when x equals infinity, u equals infinity. So I can rewrite this as 0 to infinity of 1 over u du. And we should rewrite this as limit as a goes to 0, a to c 1 over u du, plus limit, we're going to go from c to infinity. I need a different letter here. I'll say b goes to infinity of b here, 1 over u du. A couple of you did like trying to do 2 limits on the same thing. That's not very good notation. You want to split it up like this. Some of you picked a value for c, which works. I could pick any value for c, as long as c is in between my limits. I think one person in here picked, it was going from 1 to infinity, and they went from 1 to 0 and then 0 to infinity. I thought, what the fuck? But we don't want to do this, so we're going to do something like that. In both cases, we've got, this is ln of u, right? From a to c, plus limit as b goes to infinity of ln of u from c to b. So let's write out what we got. Limit as a goes to infinity of natural log of c, and I don't need the absolute value sign because c is greater than 0 at this point, minus natural log of a, plus limit as b goes to infinity ln of b minus natural log of c. We can see the ln of c cancels out. What is ln of 0? Natural log looks like this. Ln of 0 is negative infinity. Then I've got plus infinity. Infinity plus infinity, that's divergent. Which means the summing k equals 1 to infinity of 1 over k ln of k also diverges. One more real quick. Real quick. Does anyone need that up longer? Let's take a look at sum of k equals 2 to infinity. 1 over k squared minus 1. So divergence test will fail here. Divergence test, the limit as 1 of k going to infinity of 1 over k squared minus 1 is going to be 0. So it doesn't help. So instead, we'll look at 2 to infinity of 1 over x squared minus 1 dx. Yeah, sorry, I didn't realize that was last one. This equals 1/2 to infinity of 1 over x minus 1 minus 1 over x plus 1 dx. How do I know that? What did I do here? I rewrote this as 1 over x plus 1, x minus 1. And I did partial fraction decomp. That will get us to that. I would go through it, but we've got 2 minutes left, and in the interest of saving time, we're not going to do that. You can, we'll leave proof of that as verification to the student. I'm going to change the limit here because we do have an improper limit. Let's do k. 2 to k. 1 over x minus 1 minus 1 over x plus 1 dx. And the 1/2 can be inside the limit or outside the limit. Interchangeable where it goes. We saw that one of the properties of series, we saw that we can move it in, and we know with integrals it moves in and out. Natural log of x minus 1 minus the natural log of x plus 1 Evaluated from 2 to K. And half limit as K goes to infinity. Natural log of K minus 1 minus natural log of K plus 1. Minus, we'll plug in the 2. Natural log of 2 minus 1 minus the natural log of 2 plus 1. So that's 0. Natural log of 1 is 0. And we're going to have a plus natural log of 3 here at the end. What's going on in here, though? If I plug this in, it kind of looks like infinity minus infinity. That's not good. That doesn't tell us a lot. So you might want to say, what can we do about this? Well, what's the property of natural log with subtraction? It turns to division, yes. Natural log of K minus 1 over K plus 1. And then we have a plus 1/2 of ln of 3. But we saw limits can move inside shit. Because this is like infinity over infinity. That's still not helpful. Limits can move inside of the natural log. Again, this is indeterminate. Infinity over infinity. But at this point, we can use L'Hopital. This should have the same value as the limit as K goes to infinity. 1 over 1 plus 1/2 natural log of 3. And that does work. We get 1/2 natural log of 1 plus 1/2 natural log of 3. Natural log of 1 is 0. So this does converge to a value. It converges. This is not the sum, not equal to K equals 2 to infinity of 1 over K squared minus 1. Because remember, I like looking at on the Desmos, the areas were different. The integral area does not match up with the summation area. It just shows that it converges. But this converges. And we're done. Sorry, I held you back a couple minutes. I did want to show you kind of like an infinity minus infinity popping up. Peace out. I will bring your tests on Wednesday. If I remember. Someone messaged me on Discord like that day. Like Wednesday, not like at like a noon, like message me, even if you do it on Boulder, Ainsley's like Discord. In any of her channels, just ping Professor Hefe, say bring the test. Because I'm constantly checking that before her SI session in case she wants to pull up. So go for it. We're talking about Eros. And that's gonna get in your way, so I'm gonna get that out of the way. Huh?
It's like. Oh, it's like this.
It's mathematicians. It's theoretical mathematicians are like, this matters. Does it though?
Doesn't do it.
Right? The idea is infinity is not a number. So like using it there and we're doing math and the limits take numbers. So we're just gonna say it's equal a variable that equals a number up until it doesn't. It equals infinity. Again, when you're out of this class and you're going through shit real quick, you are not gonna stop to write the limit shit down. You'll just do the integral like normal and you'll go, yep, that's 0, or yep, that's infinite.
What's the same if you just pretend that you can do?
I know. I know. But if I teach you the wrong way and someone goes over and or someone doesn't pass this class and goes and takes Calc 2 again with another instructor, and they go, and you go, Mr. Jones said we don't need to do it. I'm gonna get fucking yelled at by the math department. I don't want to get yelled at. But I agree. It's fucking pointless. The problem shows up whether you put it out there or not. I 100% agree.
It's when I was like preparing for the last thing, but you just doing that, like, it's like, it's the same, you take it out and put it right back in.
Right? It's annoying.
I kind of just wanted to see if there was like. And it's, I mean, I'm super.
I'm guessing it's because it's not a real number. And for some reason, they get real picky about it. They're picky bitches about that shit. I agree with you. When I'm doing this shit and no one's looking at my work, there's no limits being written down. But I gotta teach you the right way. All right. Oh shit, that was recorded. I might have to cut this shit. No, I don't give a fuck. No, it's realistic. I did teach the right way. That was enough.